Hello, my name's Stan Mordensky, and I'm a Mendenhall Research Fellow with the Geothermal Machine Learning Research Group. The folks at GSA suggested that virtual presenters provide a photo of themselves so that the voices on the other end seem a bit less disembodied. I've done so in the bottom right here. With that said, allow me to vastly improve this slide. There we go. The overarching goal of the Geothermal Machine Learning Group is to improve our ability to predict geothermal resources in the Western United States using data-driven or machine learning methods. And that's exactly what we're going to discuss today. Now, we compare the methods that we're trying with the previous geothermal resource assessment from 2008. If you take away nothing else in the next 10 minutes, then understand that the 2008 Geothermal Resource Assessment relied upon methods that required user input to make important choices about how to handle the data. And these user choices, termed expert decisions, had as much, if not greater, impact on the models produced than the analytical method used. And lastly, and perhaps most importantly to anyone who doesn't focus on geothermal research, understand that in general, that geologic data sets are inherently large, complex, and not necessarily compliant with existing forms of traditional machine learning. And that's what I'm trying to demonstrate here on the right. If we're not careful, we can break the machine learning algorithms that we're trying to use with geological data. We must be careful. Let's take a look at the data from the 2008 assessment, and it's the same data that we'll be using with our data-driven methods later. It's important to understand that the data used for the assessment consisted of a grid across the Western United States of 2 kilometer by 2 kilometer cells, represented by the purple and yellow here. Each of those cells had data associated with it, like heat flux or distance to a geologic feature like a fault or a magma body. And each cell had a label. Either it had a known geothermal system, a positive, or it was unlabeled. We don't know if there's a geothermal system there. This creates a unique type of data in machine learning called positive unlabeled, or PU data. And it's not typical in machine learning. Typically, machine learning uses something called positive negative data. And the thing is that PU data presents its own challenges, which we're actively working on addressing. The other challenge of this data is the class imbalance. In machine learning, it's typical to have, ideally, a 50-50 distribution or an even distribution across all your different type of labels. So a 50-50% of positive to negative or positive to unlabeled. Unfortunately, with the distribution that we have less than 300 positive geothermal sites and more than 700,000 cells in general. If you do the math for every positive we have over 2,600 unlabeled points, and this creates a class imbalance that is rather extreme and needs to be addressed. With that said, the 2008 assessment did not address either of these challenges. Instead, the data were fed into one of two methods: weights of evidence or logistic regression. But let's take a second to talk about the data sets used with the methods, because how those data were handled effectively made some expert decisions. For example, with the heat flow maps or the distance to a shallow magma body or any of the other feature sets, although continuous data were available, the data had to be binned due to the tools and software available at the time. Heat flow was divided into a series of discrete bins, whereas distance to a shallow magma body was given a binary distribution. Either a cell was within 4 kilometers of a shallow magma body, or it wasn't. Now, let's take a second to talk about the methods. Although much more could be said about either method, understand that both methods are linear. In the case of weights of evidence, each input feature set is given a weight value depending upon that input feature set's association with the labeling, that is, the presence of a geothermal system or its unknown attribute. In the case of logistic regression, the input feature sets are projected against a sigmoidal function to give a probability or favorability value. Now we can take a look at the resultant favorability maps. On the left, we have weights of evidence, and on the right, we have logistic regression. On both plots, cool colors represent low geothermal favorability, and warm colors represent high favorability. What might be immediately apparent to you is that on both plots, we see low favorability. This is a product of the unaddressed class imbalance. By rescaling the favorability maps, we're better able to make out the regional distinctions on the two. Although logistic regression has greater contrast than weights of evidence, the regional patterns are roughly similar. We can make out Yellowstone, the Salton Sea, the geysers, and the Great Basin. We've covered the 2008 assessment methods and models. Now, let's discuss those of the data-driven, that would be the machine learning approaches. With the data-driven modeling, the first change is that for the input feature sets, the data sets, we no longer have to bin values. We use the continuous heat flow, continuous distance to a magma body, to a fault, and horizontal stresses. The other change that we make is that we tackle the class imbalance, and we do this using a custom test train split and cross-fold validation. We chose two algorithms for our data-driven approach, one linear, logistic regression, and one nonlinear, XGBoost. Although much could be said about XGBoost, understand that XGBoost is a series of simplified decision trees, each building upon the last. The label, the geothermal favorability, is determined through the final branches of the decision tree. And here we have the favorability maps for the data-driven approaches. On the left, we have logistic regression, and on the right, we have XGBoost. What is immediately apparent is that the favorability for logistic regression appears smoother across the mapped area than with XGBoost. And that is because logistic regression is a linear algorithm that is taking a continuous range of data and plotting that continuous data against a sigmoidal function to give a continuous range in favorability, as opposed to XGBoost, which ultimately is a decision tree. And the feature sets that are fed into that decision tree ultimately arrive at leaves, and each leaf has a distinct geothermal favorability, which is why we lose the smoothness in XGBoost. When we compare the 2008 models to the modern models, we can make three fundamental observations. The first of which is how class imbalance decreased the geothermal favorability in the 2008 models, whereas the modern models attempted to correct for the class imbalance, producing a higher predicted geothermal favorability. I've gone ahead and rescaled the 2008 models so that the regional patterns are more apparent to the naked eye. When comparing those patterns from 2008 to our data-driven approaches, we see that the 2008 models appear more similar to our nonlinear data-driven approach than our linear data-driven approach, which is certainly an interesting finding given that both models from 2008 were in theory linear. However, because the 2008 models, although they relied upon linear methods, the continuous data were binned. And by binning that continuous data, these linear methods, were effectively rendered nonlinear. Lastly, we see that XGBoost appears to have greater granularity, that is, greater variability in geothermal favorability per unit area than either of the models in 2008. And that's due to the fact that the bin threshold values in 2008 were determined by the user, whereas the threshold values chosen for the trees in XGBoost were empirically derived by the fitting of the algorithm. And those threshold values were set to maximize distinctions in geothermal favorability. Hence, we demonstrate that expert decisions have at least as much impact as the algorithm or method selected when considering geothermal data in the context of modeling and machine learning. Before we wrap up, I'd like to talk about the direction of future work. One such direction is trying to find some negatives to train from so we don't have simply positive and unlabeled data. One way of doing so is using clustering. If we cluster the data and find that some clusters have no known positives, whereas other clusters have known positives, we can take the clusters without known positives and call those reliable negatives. We then feed those reliable negatives into a supervised learning algorithm along with their known positives and ideally produce a better model. Additionally, we're working with the concept that there might be multiple types of positives and multiple types of negatives. Say, for example, should we expect the geothermal systems in the Great Basin to share the same properties as the geothermal systems in the Cascades or in the Colorado Rockies? We're also working on creating new feature sets. For example, how can we better create a proxy for permeability? I'll finish with reminding you of the underlying theme of caution with which I began this presentation. Given the unique attributes and challenges presented by geothermal or just geology data in general, we must be careful. It is too easy to take these data and throw them at some kind of method or algorithm and expect meaningful results. However, if we're careful, we can improve our understanding of the natural world. I thank you for your time, and I welcome any questions you may have.